Okay, so in this video, we will briefly introduce the idea of linear optimization in the case of two variables. So here's the problem. We want to maximize the following function. So P is called the objective function. Now here, A, B, C, D, and E are fixed constants. So they're fixed real numbers. And so our goal is to maximize the function P, given by AX plus BY, subject to the following constraints. So both x and y must be non-negative, and we may have additional constraints of this type. So Cx, so some multiple of x plus some multiple of y, is at most a given constant. We may have one such condition, we may have 2, 3, 4, or any number of them, but what will always be true is that x and y must be non-negative. So the idea is, well, how can we attack this problem first, say geometrically? Right? On the surface, it's a very algebraic problem. We're given a function p to maximize, subject to these algebraic inequalities. Well, let's try and visualize the problem and see if we can get some intuition. As we're dealing with two variables, well, we can visualize these constraints in the xy plane. As both x and y will always be non-negative, this means that we'll always be not only in the xy plane, but in the first quadrant of the xy plane. For the time being, suppose that we have two of these conditions. If you think of this as being an equality for a second, you will have a fixed multiple of x plus a fixed multiple of y is equal to a constant. This is the equation of a line in the xy plane. So this would give you a line, and depending on the sign of the three terms, this may tell you that you must be above the given line or below a given line. Assume for the time being that we have two such conditions, and they both tell us that our region must be below each given line. Suppose the first line looks something like this, and the second line goes something like this. And in both cases, we would have to be below each line. And so you see that with the y and the x-axis, and having to be below this line and below this line, this forms a closed and bounded region in the xy plane that we'll call our feasible region. And let me, right now, put bold dots on the vertices, and you'll see why very shortly. So geometrically now we have to look for a value of x and y giving a point inside of our feasible region that will maximize the function p given by ax plus by. Where do we look inside our feasible region to maximize this function? Well, this is the key question. How can we visualize the objective function within our feasible region? Well, if you think of fixing a value of p, look at the equation. A times x plus b times y is equal to a constant. This is the equation of a line in the xy plane, whose normal vector, if you remember, has an x-coordinate being the multiple of x, and a y-coordinate being the multiple of y. And so you see that the normal vector to our line, and of course the normal vector defines the slope of the line, as this vector is perpendicular to our line. What's interesting here is that our normal vector, hence the slope of our line, is independent of p. So if you think of it, you have a line with a slope defined by the normal vector n being perpendicular to your line, and as you increase p, the line moves up. As you decrease p, the line moves down. For us, since we want to maximize the function p, we'll draw a line and simply move it up and see when p is maximized. So how far can we take p so that the line touches the feasible region? So let's do a few examples. Let's suppose that the real numbers a and b define a line with a very steep negative slope. And suppose that for a fixed value of p, the line looks something like this. Well, our goal is to maximize P, so we want to increase P, so of course our line will move up. So for a larger value of P, the line would look something like this. As long as we're touching the feasible region, there will be values of x and y that will give us the desired value of P. But our goal is to maximize P. So let's see how far we can take P. So let's increase P again. We're still touching the region. Let's increase P again. We're still touching the region. And you can see the farthest that we can go is until this vertex. If you take P to be anything slightly bigger, then your line will no longer intersect with the feasible region, and so will have no solution. And so for this reason, in this case, the objective function P will be maximized at this vertex. Well, you might think maybe this is a fluke. Maybe if we change the slope of our line, maybe we'd have a different conclusion. Well, let's try. Let's reproduce this and go with a slightly smaller negative slope and see what happens. So suppose that our line now, as I've just said, has a slightly smaller negative slope. Suppose it looks something like this. Well, again, this would be for a fixed value of P. Our goal is to maximize P, so we want to see how big we can take P as long as we touch the feasible region. So if you increase P a little bit, we're still touching our region. Let's increase P a lot more. Still touching the region. Of course, all these lines should be parallel. It's just me being a little sloppy here. As again, increasing P only changes the vertical position of the line and not its slope. Increase P again, and you can see, as in the previous case, the furthest we can go is until we hit this vertex. If we take P to be any bigger, then our line will no longer intersect the feasible region, and so the problem will have no solution. And so in this case, you can see with a slightly smaller negative slope, the maximum value that P can attain occurs at now this vertex. So with a large negative slope, P would be maximized at this vertex. With a smaller negative slope, P is maximized at now this vertex. Let's do one more example where, say, the slope of our line is positive, and see what happens. So suppose that we fix a value of P that will give us a positive slope. Suppose the line looks something like this. Again, our goal is to maximize P. So as you increase P, the line will be moving up, always with a positive slope. Take P bigger, and you can see the furthest we can go again will be when we hit this vertex now. As if P is anything slightly larger, our line will no longer touch the feasible region, and so the problem will have no solution. And so for a line with a positive slope about this, P is maximized now at this vertex. And this always happened, right? You can imagine if we had more constraints of this type, the only difference is we'd have a region with more edges. So you could have a line like this, and we'd have to be below this line. You could have another line like this, and we'd have to be below this line, and you could have another line like this, and we'd have to be, in this case, above this line. So then you'd have the following region. And as you add more and more such constraints, you get a slightly more complicated region, but you can clearly see the argument will be the same. As you draw your lines and as you increase speeds, as you shift them up, whether you have a negative or positive slope, your maximum will always be attained at a given vertex, no matter how many vertices there may be. The argument is the same. And so that's basically it. So if we ever want to maximize such a function subject to these given constraints, we simply have to figure out what our region looks like in the xy plane, namely in the first quadrant, find all the points of intersections of our lines, so we have the vertices of our feasible region, and then since we know that the maximum value of p must occur at one of the vertices, we will simply have to evaluate the function at each vertex, and wherever we have the maximum value will give us our desired solution. And that's it, as far as maximizing a function of two variables using the geometric approach. There's still one question that is important. What if we had a third variable? Then we'd no longer be in the xy plane, but we'd be in 3 dimensions. And instead of lines intersecting, we'd have planes intersecting. And if you can imagine planes intersecting, and the conditions being that you're either below or above a certain plane, you'd have a 3-dimensional version of such a region. But again, you would have vertices, and the maximum value that the function will attain will occur at one of the vertices of your 3-dimensional solid. But you can imagine that geometrically, this seems like a much more difficult problem to figure out. And you can also ask, well, what if we had 4 variables, x, y, z, w? Now we'd be in 4 dimensions, and the geometry there is a little bit more difficult to visualize. And so for that reason, we will also come up with a second approach that will be a completely algebraic method of solving these types of problems. And this will be called the simplex method. In our next video, we will consider an example of such a problem. We'll first solve it geometrically, and then we'll solve it algebraically using the so-called simplex method. That's it for now.